In this video, we are going to take a look at the kinetics molecular theory. Please read the OER textbook chapter 9.3 and start homework as soon as you finish the video. This kinetics molecular theory, or what we call KMT, is going to be used to explain the behavior of gas. Okay, so in the previous video, you're looking at the relationship between pressure, volume, temperature, and also number of mole of gas. In this video, we are going to take a look at the explanation of those behavior or the relationship that we observed from the previous chapter. Okay, so the assumption that we need to make first in order to use this theory is that one, gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction only when they collide with other molecules or with the wall of container. So this assumption here is necessary because it's pretty much state that all gas would behave the same, right? So that means regardless of the type of gas, all gas should behave the same. Okay, so they are going to travel in a straight line and they are going to change direction only when they collide. And the second assumption is that the molecules composing the gas are negligibly small compared to the distance between them. So that means in this case, we are going to be able to know that the gas molecule inside the container is very small, right? So it's very small compared to the size of the container. So in this case, we are going to use the volume of the container to apply to be the volume of or the molecule of gas in there. Okay, so the third assumption is that the pressure exerted by a gas in a container results from collisions between the gas molecule and the container wall. So this one, we already mentioned this in chapter 9.1, right? When we talk about pressure, we already know that the pressure is the force that exert the surface area, right? So in this case, the same thing. So gas would have the pressure because going to collide with the wall of container to exert that pressure against the wall of container. Okay, so the fourth assumption is that gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collision are elastic. So this one is going to imply that their collision is going to be the one that involved with no loss in energy. So whatever that the energy that they originally have, once is undergo collision, is going to still have the same energy because the collision are elastic. Okay. Number 5, state that the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of gas, which is going to tell, which later on you are going to see that the speed or the kinetic energy that involved with motion, right, or the speed of the gas is going to be directly proportional to the temperature in Kelvin. Okay, so with those 5 assumptions that we see previously, we can derive 4 things out of this kinetic molecular theory. Okay, so the first one is that we can see that, as I mentioned earlier, because the size is negligibly compared to the container, so we can say that particle size, which is the gas size, is going to be small, and we can use the containers as their volume. Okay, so that means in this case, when we talk the volume of gas, you are going to assume it's going to be the same as the volume of the container. Okay, and as I mentioned earlier, because the collision happened in an elastic fashion, so therefore in this case, the collision is going to occur with the same force because the molecule doesn't lose any energy upon collide with each other. Okay, so the third one is all gases behave the same way. So as I mentioned earlier, right? So regardless of the kind of gas, all of them would behave the same way. Okay, so and we can also see that from the kinetic molecular theory, we can see that because kinetic energy is directly proportional to the temperature, so therefore as temperature increase, you are going to end up observing more movement of the gas molecule. Therefore, it's going to increase the collision frequency as well, and that is going to result in increasing the force that is going to exert against the wall of container, which is going to cause the pressure to increase as well as the volume. Now let's use this kinetics molecular theory to explain the behavior of gas as what we observe in the relationships that we see in chapter 9.2. Okay, so when we see pressure and volume relationship, we observe that pressure and volume are inversely proportional to each other, right? So as volume decrease, the pressure would increase. The reason for that is because as the volume decrease, it shrink the size of the container, right? Or the volume, again, the volume in this case is the volume of the container, okay? So as the volume of container decrease, it's going to decrease the surface area as well. So that means molecule inside of that container is going to collide with the wall of container more frequently. So therefore, that is the more collision is going to cause the pressure to increase. Okay. So with the temperature volume relationship, so as the temperature decrease, the kinetics energy would decrease as well. Molecule have less energy, so it's going to travel less frequently. Therefore, in this case, it's going to cause the volume to shrink. Okay. So with the mole volume relationship, is going to be that as the number of mole increase, right, more molecule of gas is going to increase the number of collisions. Therefore, in this case, the volume is going to increase as well. Okay, so with the pressure, temperature is going to be temperature increase, kinetics energy of the molecule increase, right? Molecule travel more, what do you call, like with higher energy more frequently, is going to hit the wall of container more frequently. Therefore, in this case, the pressure would also increase as well. Okay, so that's pretty much what of this. So lecture 9.2 that you see earlier tell you about what is going on, right? Like it's the phenomena that you observe. This one is the theory or is the model that that is used to explain those phenomena. Okay. All right. So the next thing we're going to take a look at is we're going to take a look at the effect of temperature on speed of the molecule. Okay. So what we have here is on the x-axis is the speed. Okay. So in meter per second, and then the y-axis is going to be the fraction of molecules. So similar to like a number of molecules, right? So if you're looking at, let's say like 100 Kelvin versus 1000, you can see that at lower temperature, okay, more molecule, right? So this is the number of molecules. So higher, you observe that the higher molecule is going to travel around this certain speed, right? So this is a certain speed of lower temperature. At a higher temperature, you will see that the majority of molecule at a higher temperature going to travel at this speed. And if you compare those two speeds, you will see that at lower temperature, molecule is going to travel, slower, right, than a higher temperature, because this one is in a smaller number than this one, right? So this is in a smaller number speed. This is in a higher number speed. So therefore, in this case, we can tell that as the temperature increase, the molecule would have higher kinetics energy. So therefore, it's going to travel at a higher speed. Okay, so that's what we see from this graph right here. Okay, so this is the conclusion from the graph. Higher temp, higher kinetic energy. Therefore, the molecule would travel faster at higher temp. Okay. The second effect we're gonna take a look at is we're gonna look at the molar mass of the molecule, and then we're gonna compare with the molecular speed. Okay, so again, the x-axis is the speed, and then the y is the number of molecule. Okay, so what are the difference between each of these is that we have different type of gas. So this is xenon, this is helium. Okay, so we're gonna take a look at this, right? So xenon, if you're looking at the periodic table, you will see that xenon is a lot below helium. So this is heavier. Okay, helium is lighter. Okay, so in this case, as you see, a heavier gas, right, with higher molar mass is going to travel slower than a lighter gas, right? So which is helium right here, right? So helium speed up a lot higher, 1,000 times higher, right? So in this case, that's what we see here, right? So a lighter gas would travel faster than a heavier one. Okay, so same thing, if you're looking at argon and helium as well, we will see that helium still going to travel faster than argon because helium is lighter. Okay, so that means if you're looking at this balloon right here, let's say like you start two balloons that filled up with different type of gas. One is helium, the other is argon. Again, helium is lighter than argon. So in this case, you are going to add the same amount of gas at the same pressure, at the same volume, and also same temperature as well, right? Because pressure, volume, temperature is regardless of the type of gas. So in this case, if you use the same type, you use the same number of mole of those would be the same, right? So pressure and volume would be the same. So in this case, what happened then if you let it sit like that, okay, for a while, the what you are going to observe is that the gas would diffuse out, right? So that's what you're going to observe is that helium would diffuse out faster than argon, because helium actually travel, what do you call, like helium travel faster, right? So that means in this case, helium would travel out, right, diffuse out faster than argon. Therefore, the number of mole of helium would deplete quicker, right, more than argon. So in this case, you will see that the pressure and volume of helium would decrease, and it's going to be smaller than argon. Okay, so in this case, you can see that if you let it sit in the same amount of time, you will see that helium would shrink faster than argon, okay, because the lighter gas travel faster.